Welcome to Advanced Data Analysis 1 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, I'll help get you started with Class 15 for Chapter 11 in the IMS textbook, where we will talk about randomization hypothesis testing. So I will go to the Class 15 HTML. I've opened it up here already. And in here, we've got two questions, each have several parts. So we're going to do two hypothesis tests using randomization. The Chapter 11 is here. We'll open that up and we'll learn to write the code to reproduce these methods, which are not discussed in the chapter. All right, so hypothesis testing with randomization. We have two studies here. We have a sex discrimination case study, and we have an opportunity cost study. So we'll start with the first. The background of this is the question, are individuals who identify as female discriminated against in promotion decisions made by their managers who identify as male? This is a study from 1974. And so we have male managers, and they are going to review cases for promotion of both male and female. In fact, here's the discussion of the data. The participants in the study are 48 bank supervisors in North Carolina, attending a management institute at the University of North Carolina. They were asked to assume the role of a personnel director of a bank and were given a personnel file to judge whether the person should be promoted to a branch manager position. Okay, so I think each supervisor has only one personnel file, and they're going to judge it. Okay, the files given to the participants were identical. Okay, so everyone's getting the same file, except half of them indicated the candidate identified as male, and the other half identify as female, right? They do this type of study regularly for race, right? You just change the name. You have all this identical details, just change the name of the person up top, and then the person who's, in this case, the supervisor, is going to make a decision for promotion, and you see whether or not race or sex has an effect. All right, so that's the main question. Is there discrimination? Okay. So we need to take a look at the data. So here we've got the sex of the person whose file it was, whether they were male or female. We have the decision of whether they're promoted or not promoted. And when you've got a two-way table like this, two-way meaning there's there's columns and there's rows. So there's two ways, rows and columns. And then you've got the frequencies in the middle. So we've got, of those who were male, how many were promoted versus how many were not promoted out of the total of 24. For the females, how many were promoted versus not promoted out of the 24. Now, often when you're looking at a table like this, if you see large numbers on the diagonal, that often indicates that there's some bias or some association between the row factor and the column factor. In this case, we have big number and small number. We have a big number and small number, but the relative size of these pairs of numbers are not the same, right? So we're going to see the proportions pretty soon, but there seems to be quite a big difference here. All right. So here's a visualization of the data, right? So the not promoted are the whites, and we've got males and females. So you can see only 3 and 10 for females. Okay. All right. So what we're interested in is the difference in the promotion rates. And that difference in promotion was almost 30%. Okay, so it's in terms of promotion for males, it was 21 out of 24. For females, it was 14 out of 24. If you take the difference of these ratios, you get about 30%. Okay, so that is our estimate for the difference in the population. This is what we observe in the sample that we have, but we can also make inference to a larger population of all males and females being promoted. Okay, so we're going to use a hypothesis test to make a decision between two hypotheses. The null hypothesis, as you know, is the status quo, like nothing interesting is happening, meaning that in this case, the variables of sex and decision are independent. So there's no relationship between being promoted or not versus whether you are a male or female candidate. Okay? The alternative depends specifically on the question we're interested in. And recall that the question was about whether females are being discriminated against, which would say that among the three possible alternatives of less than, equal, or greater than, we're interested to know whether females are less likely to be promoted than males. Okay? All right, so the alternative, so they are not independent, so there's some association between sex and decision. In particular, that association is that females are less likely to be promoted. Okay, so that is the type of test we're going to cover. I'm going to go quickly through the content because, one, I'm assuming that you read this. Two, there's a prerequisite to this class, which is Introduction to Statistics, and you would have learned about hypothesis testing there as well. The novel parts of this chapter are about using permutation tests instead of a t-test or a two-sample t-test or test of proportions, right? Chi-square test. All those tests make some assumptions about distributions, whether the sample size is large enough for the central limit theorem to apply, things like that. We're not going to make any of those assumptions. Instead, we're going to simulate through randomization the sampling distribution, assuming the null hypothesis is true. Okay, so if the null hypothesis is true, then the variables of sex and decision are independent. So you're not more or less likely to be promoted if, for your decision, if you're male or female. There's no relationship under the null hypothesis, okay? So we really have to put ourselves in the mindset of the null hypothesis. Let's assume that it's true and see what the consequences are. The consequence will be a sampling distribution of what the outcomes are, and how likely those outcomes are will be reflected in how frequent those results are. And then we can compare what we observed, this almost 30% difference, relative to the null hypothesis. Okay? So we really have to get our emotions out of the way, actually, because we may feel quite justified that, yes, there's this 30% difference. We see this huge gap of male and female. I'm all fired up. I'm in favor of the alternative hypothesis. But we may actually conclude that the alternative, is more likely than the null in this case. But we really need to put ourselves in the mindset of the null to sort of let the statistics speak objectively for us. Okay, so if in fact there's no association between promotion and sex, then we should be sort of equally likely for the promotion cases to be distributed among the males as distributed among the females. Okay, and maybe this particular outcome of, say, three not promoted versus 10 not promoted between the males and females, maybe that's just due to chance. Because if we had 48, coin flips, right, and I flipped the coin 24 times and you flipped the coin 24 times, we're both sort of expecting to get, for a coin flip, 50% chance of heads, we're both expecting to get about 12 heads, right? But plus or minus a bit, right? I'm not expected to get exactly 12, sort of 12-ish, right? So maybe 11 or 13 or 10 and 14. But if I were to get 24 heads, that would be really unusual, right? So how unusual is this particular outcome? So one way to do this is to shuffle, the way they're demonstrating it here, they're shuffling the promotion and non-promotion across the male and female groups, okay? So they've taken all these red cards, we'll just call them cards, and just shuffle them here. And then you can count up how many were male, how many, let's just count the non-promoted because there's fewer of them. There's 2, 4, 6 non-promoted for males and 2, 4, 6, 7 for females. So 6 versus 7. Those are pretty close to equal. That's as equal as you can get in this case. And so that seems like male and female did not have an outcome here or an influence on whether you're promoted or not. Okay. But that's just one shuffle. If you were to shuffle it many times, is this particular outcome over here of 3 versus 10 non-promoted, is that also quite likely? So that is what we are going to simulate under the null hypothesis. Okay. Now they shuffled promotion or the outcome or decision variable. You can just as easily shuffle the groups, and in my code that's what we'll do because it's a bit more generic to shuffle the group than to shuffle this other variable. But either they're equivalent, right? In fact, you could shuffle both of them. Shuffling one is the same as shuffling both. Okay. Oops, I clicked on something and it actually I clicked in this empty space, and it jumped way down. Okay, that's strange. Okay. So, all right. So upon shuffling, this was the outcome, right? And from this, you can calculate the difference of proportions. Okay. Do they do that? Yes, I think so. No, I guess they don't. But the difference of proportions here is pretty small. 18 divided by 24 minus 17 divided by 24, whatever that small difference is. Anyway, so now we're going to do this over and over and over again. Okay. Oh, here's their random shuffle. So we've started with the original data. We did a shuffle. They sorted to help you count, and then you calculate the proportion of males minus the proportion of females who were promoted, and you get 0.04 difference. Okay, so that was our first shuffle. So now we need to do that over and over again to give us a distribution of what is likely under the null hypothesis. And then we can see how unlikely was it to get something at least as extreme as what we observed in our actual data. All right, so at this point I'm going to go over to RStudio and we'll do some of this assignment. Oh yeah, let's download the QMD file. All right. Oh, it's right here. Okay. And we'll open that up in RStudio. I'm going to set the working directory to where we're going to look for that file. And then when we click open, we'll find it right away. Alternatively, you could have done open and then set the working directory afterwards. There's class 15. All right, and first thing you should do when you've downloaded this is go ahead and render it. Note that in this week we don't have any data. Otherwise, we'd have a DAT after our in our links here. So we're gonna, all the data is easy to create. So let's see, if we go back to our background jobs, it looks like it completed, and in my setup, I don't automatically open the file, but here's our file. Okay, so I will close the one that we opened on the website, and we'll work on the one that is live that we're working on. Okay, so we're basically going to go through the steps of the hypothesis test as they are discussed in this book. I pretty much agree with the way they framed the hypothesis test here. So first, you need to frame the research question in terms of hypotheses, in terms of the null and alternative. Then we're going to collect data. Okay, so we have the data already, so there's nothing for us to do there. The important part here, though, is that the data are actually collected in a way that are consistent with the type of test that we're going to perform. That is, we need to choose the appropriate test relative to how we collected the data. In this case, we've got these 48 males who are given the job of making this decision, and they're all sort of in a block because they're all in the same class, this management class or whatever it is, and so they're all sort of under similar conditions, right? So I think that this is a nice situation where you can sort of treat them as being independent and part of sort of a similar group. Okay, then we're going to model the randomness that would occur if the null hypothesis was true. This is the part I'm going to show you the code for. Analyzing the data and forming a conclusion are simple cases. So the bulk of this video is really about how do you do that randomization permutation test. Okay, so I am going to guess I'll work on this in the RStudio. Let's make this a little easier to read. Sorry, should have prepared this part. So I forget how big I usually make this, but I think I'd take the default. Okay, should be easier to read now. All right, so let's scroll down. We'll load these packages. I do have this package TikTok, which times something, because I'm going to show you how you can do something the slow way versus the fast way. Anyways, we're going to load the data called sex discrimination from the open intro package, and okay, the data have these two columns, sex and decision. They're both factor variables, and this is the first 10 rows of that. Okay. If you want to print the whole data set, you could do print n equals infinity, which will, print. Oh, come on, man. Don't autocomplete on me. I know what I want to type. Okay, print infinite number. Okay, so it printed all of them. The other print that's helpful is often width, if you've got a lot of columns and you want to see all of them. Okay. All right, so I'm just going to do a little bit of copy and paste because some of these are answered right in the text, right? So we've got the null and alternative hypotheses, which are taken directly from the text. Okay, we've got association between sex and decision. So we have no association in the null, and we do have an association in the alternative. Okay, we have to collect some data. Well, we already have our data, so let's print out what that looks like. I think that a lot of this code is in the chapter as well. So one simple thing you can do is just pass this table or our data to the table function, and it will give you a two-way table. Here's decision and here's sex. In fact, I think it's exactly just sort of coincidentally based on alpha. No, not even the alphabet. Like it's purposefully these factors are chosen factor levels are put in the order as they appear in this table. So we've got promoted and sex, 21.3, 14.10. That is exactly what we have here. Okay, so we've confirmed that we have the same data. This code right here, I'm going to walk you through what this does, and this is how to understand code that you haven't written. Okay, so we start with the data set. So I'm going to just highlight that part of the code and press Control Enter. That submits it down to the console so you can see. Okay, so that's the data. So we're going to take that and then we're going to pass that into the count function, and we're going to count sex and decision. So if I paste that down, it is counting first based on sex. So we've got the male group, and then within sex, this is a hierarchical counting. Within sex, we're counting the decision. So we've got within male, how many were promoted? 21. Within male, how many were not promoted? 3. Okay, it's the same table as this one. It's just put into long format, right? So you've got each variable or each dimension, sex and decision, as its own column, and then you've got all the unique labels, and then how many total appear from that cell. Okay, so that is what the counting does. Then we're going to pass that and we're going to group by sex. Now the data set actually doesn't look any different to us in terms of the values, but we have this additional groups that we did not have up here. Okay, and so now we have got these groups that are sex, which means that when we pass this to mutate and we perform some calculations, it's going to do the calculations for each group separately. So what we're going to do is we're going to calculate these proportions. We're going to count that n is the column name divided by the sum of n. The sum of n is where the group comes in, because when you sum, we're not going to sum all 4 rows. We're going to only sum within the group. So we're going to sum within the males, and we're going to take n divided by the sum. So n is 21. The sum of n is 21 plus 3. That's 24. Okay, and we're going to calculate that and assign it to a new column P. So let's do that. Okay, so I'm going to highlight that part of the data. It has given us a new column P. Okay, so we've got the proportion of males promoted and the proportion of males not promoted, and then the same thing for the females. Okay, and then finally, I always ungroup. This does not appear in the chapter, but I always ungroup, because if you don't ungroup and you start doing things with this data set and you don't realize that the data is grouped, that you get weird results compared to your expectations. Okay, so let's ungroup. So the ungroup takes away the group that was here. Now it's no longer grouped anymore. All right, so now we've got this new data set. As soon as I run it and assign it to this, sex discrimination props, meaning proportions. Okay, so we've got this new object, proportions. It's the original data set that now has P. And now we can calculate some differences. So we're actually doing the difference of males minus females. All right, so what is all of this? This is a way to get at just these numbers here. The promotion for males and the promotion for females. We want to subtract those two numbers. So there's many ways of specifying that. I think this is the most literate way of doing it. So we start with our data set, okay? And then we're going to filter only those rows where the sex equals male and the rows where decision equals promoted. So let's run that portion. Okay, that gives me just this one row, this top row of the data set. Then pull is a way of pulling a value from a specific column. And the value we want to pull is from the P column, and that gives me just this number here. So let's highlight all of that and run it. Okay, all of that gives me this number, 0.875. But look how easy it is to understand what that is, right? Another way to get that number, by the way, and I do not recommend this, is using indices, right? It's the first row, fourth column, okay? That's a way of getting to that number. But for one, it actually isn't a number by itself. It's actually a little table with a single value, which you won't be able to subtract. It's sort of annoying. But the other thing is, what does this mean? Like if you were to do some additional calculations on your table up here, maybe P is no longer the fourth column. Maybe male promoted is no longer the first row. So 1 and 4 are fragile. I think of them as being fragile. Whereas the labels sex equals male and decision equals promoted is very specific and will always be true. And the P column will always be the proportion, regardless of whether you add additional calculations here. So this is a better, safer way of doing it. Okay. Anyway, so we've got the male number minus. Let's do the same thing. Make sure that this female number gives me something. Okay, there's 0.583. You'll notice that those match what is in the book. And if you take the difference of these two, you get 0.29. All right, we're going to assign that to sex discrimination difference, and there's our new variable. Okay, so now we've done all of that just to calculate a single number. Congratulations, us. That is our observed difference of proportions. All right, now we need to model the randomness. All right, so here's where I'm going to start typing. All right, so make a block for our code. The basic idea here is we want to repeat a large number of times, the calculation of differences by shuffling. We can shuffle either the sex label or the decision label. I'm going to shuffle the sex label by shuffling the sex label to the outcome decision label. Okay, and for each we're going to calculate the difference, and then we need to store all those results. Okay, so that's our plan. This is called pseudocode. Right, we've sort of thought about what the process is. We've detailed each step. This is not very specific pseudocode, but we've made a plan before we started writing our code. So repeat a large number of times. So let's do reps is say 1,000. Computers are so fast that maybe 10,000 is a better. The more reps you get, the better approximation to the sampling distribution you will get. But let's start with 1,000. Sometimes I even start with even just 10 to make sure that the code works, right? Once the code works, then you can start adding zeros. All right. We need to store the results. Let's make a place to store the results. How about we've got simulation difference, okay? We're going to make a new object, and we're going to repeat NA reps times. So let's run reps. In fact, let's do this with only 10 reps and we'll increase it later. SimDiff is going to be, we're going to do the simulation and calculate the differences. We're going to initialize a vector, all with missing values, right? And then we're going to go one by one and we'll fill in these missing values as we go. All right, calculate the differences. So, well, we're going to do that after we do some shuffling. But we also need to do this iterative process. The simplest way to do an iteration is with a for loop. Okay, so we're going to start up there and then we'll end down here. And what are we going to iterate? We're going to go iReps. So that is an index. It's going to count from 1 up to 10. Okay, and so sequence length is a function that gives you a sequence of length reps. So it's a sequence from 1 to 10. Okay. There's other ways to do that. You could do 1 to reps. Will give you the same thing. I like using this function because reps may not, because there's another sequence along, which you could have like letters. Say you had like A, B, C. Sequence along gives you basically counts 1, 2, 3 for each of the items that you have in your list. So I just sort of use the same type of syntax to create this list. Okay, anyway, we're going to iterate iReps as we go through. In fact, let me just show you this. Print iReps. Okay, so each time through, we're going to start the for loop. iReps is going to start at the number 1. And throughout the whole body of this for loop, iReps is going to equal 1. It's going to do everything in here with iReps equals 1. When you get to the bottom, it's going to go back to the top, and it's going to increment iReps into the next value in the sequence, which is 2. And then it's going to perform everything in the for loop. When iReps equals 2, it's going to go back up to the top. It's going to increment iReps to the next value in this list, which is 3. And then it's going to take you all the way through with iReps equal 3 and so on. Okay, so let's just see what this does. Each time through, this is only going to print the iReps value, right? So what should we get? A print of 1, a print of 2, a print of 3, etc. So each time through, that is the iReps value in our for loop. Okay, so we've got a working for loop. What do we need to do in here? All right, we need to shuffle the label. All right, now that we're in a loop, I'm going to indent everything to help identify that from the beginning to the end, all this stuff is inside. So indentation is a way of identifying that. All right, so there's a function called sample. If we look at the help sample in the base package, okay, sample takes a sample of the specified size from the elements of X, either with or without replacement. In this case, we want to. So let's just take a quick look at how this works. Let's say we've got the numbers 1 to 10. Okay, size by default, I think, is also 10. Let's look at the replace value, or let's just see what happens when you just do it. Okay, so here's several samples. You can see that every number still appears once. It's really sampled all of them one at a time without replacement. Replace equals false. And what that ends up giving you is a permutation, a reordering. Okay, something that we will see later on in the next video with the bootstrap is that we're going to do this where you get to replace the value. So imagine you've got like 10 cards labeled 1 through 10. You pick one up at random. You look at what it is. And so in this case, we got a 2. And then you put it back in the pile. Shuffle it again. Pick up the next one. You see a 9. You put it back, and so on. So 9 and 2 are both available to be chosen again. And they are. Okay? So because they put them back in the pile, you replace them in order to resample, to sample the next value. But when replace is false, you don't put them back. So each time when you collect an 8, it's gone out of the pile. Now you've got 9 numbers remaining. The next one you pick is a 7. Like bingo, right? When you're taking balls out of the out of the roller. Okay. So anyway, so this is going to give us a reordering. That's exactly what we want. All right. So we've got our sex discrimination data set, and then we're going to mutate, and we want to sample sex. And if we assign that back to sex, we're basically updating the sex variable with a reordered version of the sex column. Okay, so let's just take a look at what that looks like. Let's just run our data set first. Okay, I guess we're going to need to print. You know what? Let's pull out just the sex column. Okay. Let's see. I want to show you what that looks like this. Okay, so start with the original data set and then pull out just the sex column. Okay, so there's our ordering, right? All males and then all females. And actually the width of the window is exactly perfect so that there's 12 and 12, 24 total. All right, so now let's see what happens when we do the same thing, but we've mutated. So we've updated the sex variable to be this new permutation. Okay. Aha. So now we've got a reordering of all the male and female labels. We have the same number of male and females, 24 and 24. Okay. And every time we'd run this, we'll get a new ordering. Okay. So we have a way of updating our data set. Let's create a new data set called DAT-SIM. And that simulated, let's not pull sex here. Okay. So we're just creating a new version of the data set called DAT-SIM where the orders of our sex column have been shuffled. Great. Now, let's calculate our difference. Well, we've done that with code up here already, right? So we counted the proportions, and then we took the difference, and we've got that here. So let's copy that code. We're going to see that this is a very slow way of doing this calculation, but we know it works. And that starting with something that works is a good plan. All right. So instead of sex discrimination, let's call that DAT-SIM. So I'm going to copy that name and I'm going to update that name. I could also do a find and replace, but there's only a few places here. I know where they all are. Oops. All right, so we're starting with DAT-SIM, and then we can calculate the proportions. Okay, in one of these samples, we have about 70% promoted and 75% promoted. Okay, and if we calculate the difference, it's a negative 0.04 proportion. Okay, so we've got our way of calculating the proportions. We don't need our print IREPs anymore. And then we need to store the result. So remember we made this vector simdiff. Okay, it's a bunch of NAs. So each time through we want to store this difference. So we need to use indexing. Is it IREPs? IREPs. So the first time through we're going to store this difference. And then the second time through, we'll store the next difference, and so on. And, okay, calculate the differences. We've sort of done that up here. Okay. Okay, well, I think we've got code that works. Let's give it a try. We'll highlight everything and run it. And it went pretty quickly. It's all done. And if we look at simdiff, these are all the differences for our 10 reps. Okay. Finally, we can have a sense of what this distribution looks like by making a histogram. So let's pass that to the histogram function. Okay. There they are. All right. And I'm going to increase the number of bins in our histogram because pretty soon we're going to increase the reps. Okay. So now we've got some code that works. Let's run 1,000 of these. Okay. Now look how it's sitting there as it's counting, going round and round and round and round. So let's time how long this takes. and then I'm going to show you a faster way to do it. Okay, so using these functions tick and talk from the TikTok package, we can time the event. But here's our sampling distribution based on 1,000. Okay, it's centered at 0, and it's roughly symmetric, and we're going to make a comparison pretty soon. So let's run this whole piece of code again. The TikTok is timing just the for loop. Okay, so it turns out that taking the data set and then running it through this count, group by, mutate, ungroup, that takes a long time, and it's an inefficient way of doing it, but it is very literate, meaning it's easy to read this and understand what's happening. So that is this 15 seconds. You know, maybe is good time well spent because you can understand the code. I'll just show you a faster way to do this specific thing, and there's almost always a faster way to do things. The other thing is we don't need to print those intermediate results. Okay, so let's comment out all of this. So this is, you don't need to do this, okay? I just want to show those of you who are more computer oriented, like what we could have done. Okay. In fact, let's put this as a comment as well. Okay. Okay. We're going to. All right. So first of all, we've got this table. We've seen this already. .sim. When you pass that to the table function, made this two-way table. Okay. Now I'm gonna just for I don't know, does it matter? Yeah, it sort of matters. I'm not going to use this pipe just because it's going to make things a little easier. In fact, there's some things you can't do with the pipe. So anyway, so here's the table. There's also a function called prop table, which gives you proportions. If you give it a table, it will calculate proportions. So let's wrap our table in prop table, and the default there is to make all the proportions equal 1. But there is an option here for margin. So margin, you can specify which way should you get proportions. And if we specify margin 1, 1 are the rows, margin 2 is the columns. So now across the rows, the proportions sum to 1. So that means I've got my male promoted proportion and my female promoted proportion. Those are the two numbers that I need. Okay. From there, I can pull out, it's the first column that I care about. So I'm going to index, I'm going to pull out just the first column. There's those two numbers, 0.75, 0.708. Okay. And then there's a function called difference, DIFF, which will calculate the difference of these two. Now you notice the way the difference function works is from the base package is it calculates the second one minus the first. And that's because we're often using the difference function for many values, and we want to see how things changed. And when you go from today to tomorrow and you want to know what the change is, that change is equal to tomorrow minus today. So that's the next one versus the first one. But our calculations have been always male minus female. Okay? Well, one way to reverse this difference is just to put a minus sign in front. So now we've calculated male minus female. And this label is not important, but the number is. But we've now done this big calculation. That is the difference that we want. Okay? So let's remind ourselves that the slow way took 15 seconds. Okay? Let's repeat the code, but now we're going to use this faster calculation and see that it finishes in 1 second. Okay? So I'm just showing you that there's multiple ways to solve the problem. When you have a big problem where you say had, you know, maybe instead of 1,000 reps, you needed to do 1,000,000 for some reason of precision, and each of your data sets was very long or very large, right? So in that case, running, say, all this code in this way might end up taking 4 hours. But if you think of it in a more clever way, maybe it gets done in 5 minutes. So furthermore, there's ways of doing parallel processing on for loops. See the package for each, or look at the parallel package for ways of doing parallelization. Okay, all beyond the scope of this lecture. Okay, but anyway, here is our sampling distribution. It looks great. You know what? Now that we've got a fast way of doing this, we can do, you know what? This distribution looks great. I don't really need to up the reps, but let's just take a look at what the reps does to our histogram. Okay, so here is, well, we increased it by 10, right? So it took 1.2 seconds the first time, so it should take about 12 seconds to do 10,000. Okay, that's about right. And so this basically looks just as good as the first one, right? So 1,000 was fine. However, if you get down to 100, we'll see that the shape of our histogram starts to suffer, right? It's not really smooth anymore the way we want it to be. So 1,000 is about right. You can probably get by with even, maybe 200 or 500. Okay. Okay, this looks great. So now we want to analyze our data. That means how, oh, by the way, in each of these, I should probably be writing a little bit of a sentence or something. So you might discuss a little bit like what the plan is and how this was done. Okay, so you write a few sentences about that, and then you can say see code below. Okay. From our discussion, I think you can figure out what to write. Analyze the data. So here we want to compare our observed sex difference, which is 0.29, which is way out here in the tail, right? Compared to what the distribution looks like under the null hypothesis. These are the reasonable values to see when the null hypothesis is true. Basically, values close to 0. Maybe even as far as roughly 0.2, but 0.3 is pretty far, and that's what we saw. All right, so to calculate or to analyze the data, let's take a look at, let's see, so how unusual is our observed difference compared to the distribution of differences under the null hypothesis? That's what we want to ask. All right, so how do we calculate that? Let's give ourselves a code chunk. Sorry, I know that there are shortcut keys for this, but RStudio is not how I do most of my coding. So we want to calculate a p-value. That's the probability of being at least as extreme as what we observed. So we've got what we observed, our sex discrimination difference, and we want to compare that to all of our simulated differences. Okay, so we've got the simulated differences, and we want to see how many of those are at least as extreme as what we saw. Okay, so how many are at least as big? So if we perform this comparison, here's a true, here's a true, we get a bunch of trues and falses. Now, when you do calculations with trues and falses, falses numerically, falses are 0 and trues are equal to 1. Okay? So if you sum this up, it will count, sorry, it will count how many trues there are, 27. Better than that though, because you've got zeros and ones, if you calculate the mean, that takes the number of true values, the number of ones, divided by the total number, 1,000. So that is a proportion. In fact, proportions are means of zeros and ones, where the 1 is a success. Okay? So here is the proportion of true values, and in that case it is the p-value. All right, so now we can write a sentence about this. So it appears that a difference of at least, let's see, so of at least this difference here. Okay, so let's make R print this for us. If we put in single ticks an expression like this, it will print that number in the text if we interpret it with R. So these left ticks are called inline. We're giving an inline code chunk. The code chunk is going to be interpreted by the R language, and then whatever follows is the command. The only thing I would add to this is that we don't really need 7 or more digits of in our plot. So I always pass this through signif of 3. So we have 3 significant digits. Okay. That also means that if you got something like with lots of zeros in the front, it will keep the leading zeros and give you 3 significant digits. Okay. Anyway, I've got a book chapter about data visualization, and we talk about significant digits, and 3 is usually the right number for the most that humans can really sort of hold on to and think about, but also that you rarely have enough data to have results precise enough that you'd have more than 3 significant digits in your measurements. Okay. So anyway, so it appears that a difference of at least, so this is 0.292. Let's see, under the null hypothesis would only happen about how often? Well, that has to do with the p-value. So we've got the p-value, and we'll also make that 3 significant digits. Okay, it only happens this often. Now, a lot of people would prefer to see this as a percentage, because we often think about things in percent of time. So you might take 100 and multiply that to the p-value. Okay, so but then you've need a percent sign, because percent sign literally means percent per 100. So we multiplied by 100, and now we divided by 100 with the percent sign. Okay, so that's going to say 2.7% of the time. Okay, so it appears that a difference of at least 0.29 under the null hypothesis would only happen 2.7% of the time. Okay, so is that a lot? Such a low probability indicates that observing such a large difference from chance alone is rare. Okay, so that probably means we can form a conclusion about how rare that is. In this case, we reject the null hypothesis in favor of the alternative hypothesis. Okay, so that's our decision. You will recall from your intro stat class that we usually use a specific threshold of, say, 0.05. It's called our significance level. And if your p-value, right here, is less than 0.05, then that's evidence against the null hypothesis. Okay. Basically, the p-value is a measure of how consistent the data are with the null hypothesis. And if it's greater than 0.05, or 0.05 and more, I should say, that's data that are consistent with the null hypothesis. And if it's smaller than 0.05, then we decide that the data are inconsistent with the null, and so leading us to reject the null in favor of the alternative. So in that case, we have rejected the null in favor of the alternative. Let's write what that means in the context of the problem. often you can just go right up to your alternative hypothesis because you've already done the work to get these details. So let me just copy that without thinking about it, paste it here, and now we'll read it. Okay, so what does it mean? The variables sex and decision are not independent. The difference in the promotion rates was not, I have some typos here, was not due to natural variability. The equally qualified female personnel are less likely to be promoted than male personnel. Yeah, that's what the data say. All right. Well, that is an hour. And with that, I believe that you will be able to complete the same process for the opportunity cost case study. Let me look at, I think I've got a typo here. Yeah, right here. Rates are not due. Double underline or double star gives you bold. Okay. Okay. The rest of it looks okay. Good. Let's render this and see what we get. Now, if your code still runs the slow way, the render process will take a bit longer. We only have 1,000, so that should be pretty quick. All right, the background job's completed. Okay, let's go and refresh our page and see that we got output for what we've done. There's our data set. Here's our table. There's our table. Here's our sex difference. Now, it might be nice to write a sentence here about the observed difference is 0.29. Okay, the model of randomness. So describe how we did this. You can sort of go based on the pseudocode that we started writing at the beginning. You don't need the tick and talk. Okay. If you do want it, however, go ahead and install the package here. Okay, back down. So here's our histogram. That's about the variation under the null hypothesis. Analyze the data. Okay, let's see how our code works. It appears that a difference of at least 0.292. So that is right here. It appears that a difference of 0.292 under the null hypothesis would only happen about 2% of the time. Okay, so that's this percentage here. And these numbers, by the way, are going to change every time that you run it, unless you set a random number seed, because it's doing 1,000 random permutations. So you'll get 1,000 different results, and when you average them together, you'll get a slightly different percentage. Okay, so that's okay if it doesn't match. It should be pretty close to this, though, right? I'll run it one more time so we can take a look. In fact, let me go render it, and then I'll refresh this page in a moment. Such a low probability indicates, okay, good. And then the rest of this looks good too. All right, so let me refresh this page now that this new background job has completed, and we'll see if this number changes. 2.6. Okay, and we get a slightly different histogram as well. We'll run it one more time and take a look at how the histogram changes. This is not that interesting, I would say, but we'll just see it. Okay, so that finishes. So let's look at our next sample. Boom. Okay. So don't worry about these numbers changing, but sort of around 2.5% is probably about right. All right. So I think with that, you'll be able to complete the opportunity cost case study. It's a similar type of study. You'll need to take a look at the chapter to get the context for the study. Scrolling down, there it is, opportunity cost case study. Okay, so take a look at the null and alternative. You can just copy and paste these null and alternative hypothesis text right into the document. Okay, make sure you read what the data are, and and verify that you can make this table, etc. Let me see if there's anything else that is sort of unique to this example from the solutions that I wrote up. I think it's exactly the same, actually. Yeah. So we never went ahead and made this particular plot, this bar plot, but it's not needed either. Okay. Okay. So there's their sampling distribution, their observed difference is up here somewhere. Looks like maybe 0.2. Yeah. So they've got 0.2. Here's their sampling distribution. 0.2 is way up here. So they'll have a small p-value in the second example as well. Okay. All right. Very good. Well, I hope that helped. And I would say that the main point of this video, if I had to summarize the main thing that you got out of this, is taking the randomization test and actually writing this code, right? The main concepts here are always have a variable that is the number of replications rather than putting it as a number in your for loop, so that it stands out and it's easy to change. And then because that number 1000 appears here for where to store the results and for how many times to loop. So it appears twice, so just create a variable up top. Always pre-allocate space for your results, because that will also make things very fast, right? It's like figuring out in your house, like, where do things go so that you don't just have chaos. Make a place for everything and then place the things where they go. So that's what we've done. We started with a list of missing values rather than zeros. Don't pre-fill it with zeros, because say your for loop only runs halfway and gives you an error and you don't catch it, and then you decide to run the code after it. Now you've got a bunch of zeros in there. Zero is an actual number, and it could be confusing compared to what the true data should be, right? So, but if you fill it with not available, missing values, then if you have NAs that there's a problem and it didn't actually compute a number. Then we talked about the for loop and going around and around. Then the main thing for the sampling is just the permutation part, and then how to calculate the difference. And we did that the slow way, which was nice because we just copied the code from above and it worked. And then I showed you a faster way to do it, which is not important, right? But if you are new to programming and you have for loops are historically or notorious for being very slow. There's almost always a faster way to do something if you've got something in a for loop. So a good programmer will be able to write a for loop, but then be able to think more critically and find a faster way. But I would only bother finding a faster way if it's important. In this case, it's not important. What's 12 seconds, right? And you'll have 12 seconds twice because you've got these two. Now, if you run it this way, as we saw, it was like 1.5 seconds. Okay, so it's a bit faster every time you click render, but that's not the long part of the assignment. The long part of the assignment is thinking about it and writing the answers. If it takes a little bit longer to render, you're only rendering it a few times. It's not a big deal. But if this was in production and you needed this to run fast 1,000 times a day, talk with a computer science friend or someone else who does statistical programming regularly, and brainstorm a way to make things faster. Okay, and the last part is just inputting these values into the text directly from the code that we wrote. All right, well, see you in the next one.